welcome, and in this final part we would be looking at the hardware implementation for the different forms of the cout and sum. So cout is actually equal to a dash b cin plus ab dash cin plus ab cin dash plus ab cin, which after the application of the postulate is equal to a c into ab dash plus a dash b plus ab. We also had derived this form using the Cape map, and it was equal to ab plus a plus b into c of n. Now let's look at the hardware implementations for both of these parts. First of all, let's talk about the general form. Since it's using the a dash and b dash, now we have to generate these literals plus c of n. So the first term we have, now let's implement it using two input gates. So the first term, so this is my a, this is b, this is cn. So the first term could be generated by ab dash, since it is equal to let me show you. So the first term is ab dash, so this is a, this is b dash, so this would give us ab dash. And in order to generate the full term, it has to be ended with the cn, so this is ab dash cn. Similarly, the second term would be generated using a similar combination. So here we have the a dash b, so it is a dash b c n. Okay, and these return should be odd, so this is what we have. And similarly for the next term, we have to pass it through an AND gate, and then both of them should be passed through an OR gate. So this is basically our cout. Now let's implement the derived form. And for this derived form, since we do not need the complements, so I'm not going to make them available for this implementation. So now let's change the color for a moment. And if we implement them, so this would be AB, the first term. Then we need A or B. So this would be A or B, which has to be ended with the Cn. So this is A plus B into Cn. And all of them would be passing through the OR gate, and we would get the second form that's complemented. So it would be cout. Now if we look at the comparison for the first implementation, the total number of the gates that we used are 1, 2, 3, 4, 5, 6, 7, 8, and 9. And here we are using 1, 2, 3, and 4 gates. So we are getting advantage of 5 gates in the second implementation. Okay. So now let's talk about the second implementation, of which is about the sum. Okay. So for sum, again we had two types of the terms. So generally the equation for the sum is S is equal to AB Cn plus A dash B dash Cn plus A dash B Cn dash plus A dash or A B dash Cn dash. Okay. Now let's first implement it. Since we need the complement of all the inputs, so I'm gonna add the NOT gate to all of these inputs. So this is what we have as the input. So this is A, this is B, this is C, N. Okay. So the first term is ABCN. So this would be A, B, and they have to pass through Cn. So to give us the ABCN term. Okay. So let me add the connection there. For the second term, it would be A dash, B dash, and then it has to pass through the Cn. So it would be A dash, B dash, Cn. Okay, now let's add an OR gate here. Similarly, for the next terms, it would be A dash, B, which has to be ended with the Cn dash. So this is our A dash B Cn dash. Similarly, for the fourth term, let me make lengthy. Okay, so here we would have A. So this is A. This is our B dash. And finally, we have to end it with the Cn dash. So this is A, B dash, Cn dash. Now let's pass them through the OR gate and finally combine them with another OR gate. Okay. So this is basically the first implementation. Here we are using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 gates. Okay. Now let's talk about the second type of the implementation, which is about the form that we had derived. So it was in fact S is equal to A plus B plus Cn into C out plus A, B, and Cn. Okay. So for this form, we in fact do not need the complementary input. So I'm not gonna make this line lengthy for that. Okay. So just to remain compatible, let me make them lengthy. Okay. So now let's implement this second form, and for this form, okay, we also need another input, which is C out. Okay, so let me create another input here, which is C out, but we need the complement of it. So this is how we have generated the complement. Now let's implement this equation. So first of all, it is A plus B plus C in plus C out. However, let's write explicitly what this C out is. So C out is in fact AB plus A plus B into C in. Okay. Now let's first implement it. So it would be A, B, so this is the first term generated, then A or B, this is what is generated, into Cn, and now both of these terms are generated, they have to be added together. So now we got C out here. Since we got C out here, so this C out is also appearing here, and we have to use the complement of it. Okay, so now complement the other parts of the equation. So here A plus B plus Cn, so in fact it would be A plus B, and we have to OR it again to get A plus B plus Cn, and then they have to be ended with the C out, so I have to use an AND gate there. Okay, so in this way this first term is generated. For the second term, let's add AB into Cn. So for that, this is A, this would be B, and this would be Cn. And now if we use another OR gate here, we would get this S bar here. Okay. So now let's compare the two types of the implementation. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gates. Okay. So here we have the 11 gates for the implementation of this second form, while previously we needed the 14 gates. Similarly, for the C out, we got the advantage of the 5 gates. So overall, if we look, then the total advantages of the 8 gates using these minimization techniques, using the K-map and the other implementations for this single bit full adder. If the number of the bits are increased, then we actually would get more advantage in the hardware. Similarly, if you look here, then there are few terms which are being repeated, and if we use this information as well, then we can get further minimization of our hardware. So thank you very much.